Hello guys, yeah, another video here today, and this is going to be a microcontroller based video. And yeah, from what you can see on the screen already, you can guess it's about the ADC, the analog to digital converter. And this circuit is just meant to show how the ADC works, like a very basic version. And of course, you can implement it later for more actual applications, but this is just meant to show how it works. So yeah, basically analog to digital converter, as it says in the name, it converts analog signal to a digital one which you can store. And here this diagram shows it very nicely. How you do that is basically by sampling and discretizing. So what sampling is basically, you can see here you have this analog signal which is varying continuously with time, and you can't store a continuous value, right, in a microcontroller. So what you do is you sample it at a fixed time interval. So let's say you take the first sample, and let's say your sampling frequency is something like 1 kilohertz. So every 1 millisecond basically you measure the value. So 1 millisecond, 2 millisecond, 3, so on. Of course, depending on what your switching frequency is, this sampling would change. If it's a very fast changing signal, you would have to increase it, but if it's something like very slow, then yeah, maybe like 1 kilohertz or maybe even lower. But yeah, you measure its value and then you store it. And how it does that is basically depending, each ADC has it's generally a n bit ADC. That means how many bits it is. So let's say the microcontroller which I'm going to be using today is the MSP430, which I've used in the past. It's a nice 16 bit microcontroller, simple one. So this basically, you can see here, if you go down, okay, I guess that's in the other data sheet, but basically this, yeah, here you can see it. It has a 10 bit 200 kilo samples per second ADC. So you can see 10 bit, right? So basically what 10 bit means is 2 power 10. If you do, that's basically 1024. And that basically means that your analog signal, and since this is a 3.3 volt microcontroller, basically that's its maximum range. Of course, you can change the reference depending on what your analog reference is. Your digital value would change, but basically your 0 to 3.3 volt signal, which you scale down, this signal, let's say it's between 0 to 3.3 volts, that would get translated to 0 to 1023, and not 1024 because it starts from 0. So 10 to 2 power 10 minus 1. So that's going to be your digital value, and that's going to be much easier to handle in your code. So yeah, that's basically what it's going to do. It's going to give it levels. So you can see here, this was here, so this got discretized to somewhere like this. So this is maybe, let's say something like, this entire thing was 3.3, this is somewhere around the half point, let's say 512. This is slightly higher, say something like 600. It goes down maybe 400, and here it reaches its peak. It's maybe it reaches 1023 itself. So yeah, that's what it basically does. It converts it into a integer value depending on how many n bit of your ADC it is. Let's say if it's something like a 12 bit ADC, it would be 024095. So yeah, that's how it is. And now to just show how the ADC is detecting and like a basic code setup, I'm just going to show you the code here for the MSP430. And yeah, it's in Code Composer Studio, which is the standard IDE. So yeah, I'll just run through the code once. So what we do is basically, first is just setting up the clock. I'm just setting 1 megahertz standard, and I'll talk about this later, what all these pins are. But let's first set a timer, because I said, right, you have to sample it at a time interval. So you need a timer for that. So here I'm just setting up a timer, and since it's 1 megahertz, 1 megahertz by 1000, that's basically 1 kilohertz. So it's going to sample every 1 millisecond. And yeah, that's basically what the timer is. If you go down here, the timer, it will generate an interrupt, and after that it's going to start the ADC conversion. That means it's going to measure the value using the sample and hold capacitor which is there internally, and then yeah, the conversion ends and it stores the value basically. And another thing here is we have another function here, the ADC, that's basically to set up the entire ADC. And yeah, as I said, you can choose different references. It's not necessary that you have to use 3.3 volts as your peak. Just like here, for example, I haven't used 3.3, I'm using a 2.5 volt reference, and this exists internally in the in the MSP. They have this ready, so you can use that. Basically, you can map 1023, which is your maximum value, to 2.5 volts. So that's what I've done. And this is a reference, right? It's an internal reference. It derives itself from the 3.3 volts which is supplied from your USB or whatever power source you're giving. So it does need some time to set up. That's why I've given like a 1 millisecond delay here. You can probably increase it, but this should be fine. And yeah, after that, the internal reference would preferably be ready. The 2.5 volts needs to be ready, otherwise you can get some improper reading. So yeah, the delay is there. And yeah, I'm going to be using the P1.5 port pin as the ADC point. We're going to be measuring the signal there. And rest of this, just to show, like confirm that our range is within that, what I've done here is I'm using 6 port pins on the second port, and what I'm going to do is I'm going to connect 6 different LEDs to each of these pins, and depending on what voltage range is it's in, which is what the code is here in the while one. Let's say it's about 1000, which means it's about 12 volts. We would make the this pin high, which basically would mean that LED would light up. Similarly, if it's this comment is wrong, yeah, basically if it was between 9 volts and same 12 volts, another LED would light up, and the other ones, each one of them I'm turning them off. So basically only the one voltage which it is in at that point, it's gonna light up that LED. So similarly, this is for 12, about 12 volts, this is 9 to 12 volts, this is 5 to 9 volts, and this is 3.3 to 5 volts, and this is 1 volt to 3.3 volts. So I'm just giving arbitrary ranges just to show how the precision is. And if, yeah, this is the final one, 1 volt to basically 3.3, and if none of this is true, it's just gonna light up the final pin. So yeah, that's basically what the code is. And the ADC also has a interrupt setup, so that after its measuring is done, it will store the new value here. And yeah, that's basically what this is. And now let's go to the circuit. So yeah, this is the setup, and you can see here that's the MSP board, the development board, and I have it plugged into my computer. And this is just the small circuit here. Basically, as I said, we're going to be measuring from 12, basically roughly a 12 volt signal. That's going to be the maximum voltage, maybe 13 volts. And so of course we know the ADC range is maximum 3.3 volt, and that too here we are using a 2.5 volt reference, so even lesser. So of course you have to use a resistor divider or you will destroy your microcontroller. So here I have a resistor divider of basically 39k and 10k setup, and we're going to be measuring across the 10k. So of course by the voltage divider rule, it's going to get a smaller voltage. And after that I just have a series 1k after that, which is not really needed, but just for secure overcurrent protection I have it there. And additionally I have, you can see that there's a diode that is basically a Schottky diode, and it's a clamping diode, just in case if there's some kind of over voltage event, which shouldn't happen, but for safe case, it will basically clamp the voltage at the ADC, because you know if it goes above, as I said, above 5 volts somehow, it's going to destroy the ADC pin, right? So this will basically clamp it at that, and it's placed between the ADC pin and the VCC pin, which is at 3.3 volts. So that is there. And finally there's a 100 nanofarad just to reduce the noise across the ADC pin. So yeah, that's the connection, and that goes inside, as I said, the A5 port we are using. It's going to measure, and all of these other wires are for the outputs. You can see here I have them from red, orange, yellow, blue, green, and white. And red is basically going to be our about 12 or 12.5 volt. This is 9 to 12. This is 5 to 9. This is 3.3 to 5. This is basically above 1 volt. And you can see here this white LED is currently lighting, and as I showed you in the code, if it doesn't measure anything, and you can see here why it's not measuring anything is because I haven't connected this yet to the power supply, which is going to supply the 13 volt thing. So right now it's just lighting the default LED, which is white. And now I'll just connect the power supply, and you can see immediately that it will jump to the green, because we're going to be measuring something like 2 volts. So let me just connect that. And yeah, you can see the green one is lighting, and currently I'm at 1.97 volts, and as I said, above from 1 to 3.3 the green one is going to glow. And now I'll just vary this. It's just a basic DC power supply, so we're going to be varying it, we're going to be seeing how the colors change. So let's go to 2.83, and you can see it's still green. So maybe I'll do a common view here, so you can see yeah, that's probably okay. 3, and you can see now we're at roughly, there's a flicker because that's the transition point, so both are sort of glowing. and now you can see we're clearly above 3.3 volts. We're at 3.7, and now the blue one is glowing, the rest of them are off. So we know our ADC logic is working. Let's continue. Let's go to the next threshold is going to be 5 volts. So now we're close to 5 now, and yeah, the flickering has begun, and yeah, now we're above 5 and the yellow one is lighting as expected. And let's continue. Next threshold is 9 volts, so I'll do it a bit faster. And yeah, we're at 8 volts now, and now as we approach 9 volts, yeah, now we're at 9 volts. You can see that yeah, the transition has begun, and yeah, now the orange one is lighting, yellow has turned off, and last one is about 12 volts, right? So let's go about 12, and orange is still on. Yeah, now we're at 12.4 and 12.6, and yeah, now we're at 12.8. As I said, close to 13 is what I designed it for. So you can see here now the red one is lighting, and you basically saw how the one after the other it turned. So yeah, white, then green, yellow, blue, yellow, orange, and red, and that's exactly what we wanted. You can make sure that your ADC is working. This can be a sort of a test program to make sure that your ADC is working and your basic code is right. So later you can probably apply it to a closed loop converter in power electronics, which is what I'm going to be doing next. We're going to be doing the closed loop buck converter soon. So this is just in prep for that. So yeah, just to show you the colors again, yeah, we're back to green. So that was the whole ADC setup, and yeah, as soon as I remove it, we're back to white because we removed the power supply. So yeah, I hope you like this basic circuit and probably learned a thing or two about ADCs. And yeah, thank you.